Okay, so hopefully this is recording now, and let's get right into it. Remember, this is I forgot which one it was. It's probably Winter 21, the Winter 21 final exam. Let's begin with the first question. What value of c makes the period of the signal 1 plus cosine of ct squared equal to 6 pi? And so for this initial question, um, it is important to note that this, or actually maybe it's easier to expand. So my first thought is to expand this to its full form as such. And at this point, it's actually important to note that this, maybe it's better, but to kind of draw it out. But so this we really don't really care about. This will look like that. Let me actually, this will look something like this with period um, 2 pi over c. And this this will have period of pi over c. This is just a universal truth. This is like cosine, like knowing kind of how the behavior of cosine squared of ct will significantly help with this problem. And I feel like everyone would be familiar enough to kind of notice this. And so noticing this, we realize that the period of this will always be bigger than this one. And so, um, and furthermore, the period of this, so note the period of cosine squared ct is 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 like a direct multiple of it. So it's 1/2 period of our other function. And so kind of all we need to do is uh is kind of work with this one, and then this one will kind of like interweave itself between the graph of 2 cosine of ct. And so what does this mean? This means that um all we need is uh is 2 cosine of ct to have period, that's 2 ct. We need to have a period 6 pi, and thus we just need c equal to 1 over 3. That's it. Um, of course, this kind of comes from the fact that like if you add two periodic functions that are multiples of each other, then all you need to do is kind of work with the one with a larger period, because the smaller period, like let me give an example. If I just as a nice little example, we if I have a blue function, if I have a red function like that and a blue function like this, it's very easy for us to realize that the period of like the period of f of t plus g of t the period will take um, the period of f of t because it's larger, as in like the periodicity is contingent upon the repetition of both functions, and since f of t has a larger period, and g interweaves itself in between each g of t happens twice for each f of t, and so we kind of just work with f of t in order to obtain uh, like our desired period, and that's how we conclude that c equals 3, c equals 1/3. Again, please feel free to interrupt if you have any questions, but otherwise I'm just gonna keep blasting through. And I will give motivating examples as we go through. What is the impedance of a circuit parallel combination of a 5 microfarad capacitor and a 1 microhenry inductor with a 500 kilohertz sinusoidal signal voltage across it? And so let's kind of just check, let's kind of just write it out. So we have impedance, parallel, capacitor, and inductor. And so clearly we are taking just complex numbers, but boom, 5 microfarad, and this is 1 microhenry. Well, impedance, the impedance of this, C equals L, the inductors are L. Wait, yeah, sorry. Then ZC is equal to J omega C. No, sorry, 1 over J omega C, which is equal to 1 over, well, we have 500 kilohertz. So usually I just like to write this as like just negative J, and then I deal with the fraction just almost never. We have 500 kilohertz. So 500 times 10 to the 3. And then we have 5 millifarads, microfarads. Someone tell me if I'm wrong, but micro should be 10 to the negative 6. And so what we do obtain is this is negative J of 2.5. Actually, maybe I'll just keep it like this, times 10 to the negative 3. But then this is 2.5 times, that's just 2.5. What am I saying? Negative 2.5 J. Splendid. Furthermore, ZL is equal to is J omega L. J 500 times 10 to the 3 L, which is 1 times 10 to the negative 6. And let's just keep cooking. We just have J 500 times 10 to the negative 3, which is just equal to 0.5 J. Yeah. And so now, and we know that we want to find the equivalent impedance, which means that ZQ is equal to this. And all we need to do, this, and all we need to do is kind of just work it out. So we get negative 1.25 J over, sorry, hold J's together, so it's J squared, so it's just this, over negative 2J. And thus, what we obtain is, this is 5/8. Wait, hold on. Clearly, oh, I kind of messed it up. I forgot to convert it into, yeah, thank you. I forgot to convert it into omega 2, yeah, 2 pi f. Sorry. Oopsies. Completely forgot about that. Well, that's okay, because all we need to do is kind of just work around with all of the, oh my goodness gracious, I kind of forgot about all this. Sorry. I really just ignored a lot of the intricacies of normal algebra. Can't believe it. But that's okay. We have 2 pi 500 times 10 to the 3. And what was it? 5 microfarads, so 5 times 10 to the negative 6. There we go, that's okay. And then keep going, 1 divided by, it's just 2 pi times 2500 times 10 to the negative 3. And then what we can convert this to is negative J, sorry, maybe I'll keep the 1 over 2 pi over here. And then we can, this will be 1 over 2.5, which is just 5/8. No, 2.5. 1 over 2.5 is not 5/8, it's actually 2/5. Thank you for correcting. And then I could actually furthermore convert this into negative j over 5 pi. There we go. Okay, and then I forgot my 2 pi over here as well. That's okay. I think this stays mostly consistent though. We should just get pi j. Hopefully if I made any mistakes, someone can catch it. But essentially, hopefully thus far this is right. And then now I could continue with whatever I had before. I multiply these, so the numerator, I multiply those together, and I obtain 1/5. I'm pretty sure it's 1/5. And then the denominator, I add them together, and that doesn't actually look as easy as what we just had before, but that's okay. So we can pull this out, and then multiply top and bottom by pi. So we have pi over pi squared j minus j. And so, I can factor out a j. Factor out a j now, and that would be negative j over 5 pi over pi squared minus 1. And so we have, at putting everything together, we have the following answer. And hopefully I didn't make any algebraic mistakes. I clearly did make an algebraic mistake somewhere. Oh, I forgot. This is not just, actually, yeah, that's actually fine. This is just pi j. Hold on. J omega c, that's good. Over 2 pi f, it's fine. Kilohertz, it's correct. 5 microfarad, so that's good. That's fine. This is 1 over 2.5. Yes.
When you move the J up for the impedance for the capacitor, you should get rid of the negative, right?
Why is that? Because I moved it up because 1 over j is equal to negative j.
Oh
Which,
wait, no, you're right. You're right. Yeah, I can't find it either.
yeah, hold on. I'm pretty sure I could debug it really quickly here. I just need to take a good long look. Take a 2 pi.
It's supposed to be 10J, isn't it?
No.
This is fine. So this is fine. Find the multiple of this. That's good. Negative 3. That's just 1/2. Yeah, this is fine. Okay. That is rather odd. Multiply those two, get 1/5 over. That's good. Multiply top and bottom by. Pi squared. Yeah, that is. Oh, when I factor out the 5, I need a 5 over here. Or I need a, yeah, I need a 5 over here. There we go. Okay. I found my mistake. There we go. And so I actually don't need this. Hold on. Whoa, 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 whoa. No, 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 no. I multiply top and bottom by 5. Never mind, actually, that's fine. Wait, that's fine. No, never mind. So this system exists. I factor out a j. It's fine. Huh. That is weird. I'm off by a little. I'm just off by. Oh, it's because I got rid of the j. Wait, did I? Yeah, I got rid of the 5 here, I think. Yeah, I got rid of the 5 here. I only multiplied by pi. Yeah, I multiplied top and bottom by pi, not 5 pi. So I forgot to keep this numerator down here. Okay, okay, there we go. Yeah, that's just a little bit of rough algebra. And so what I obtain is pi over 1 minus 5 pi squared, and then j. There we go. Yeah, sorry about that. That was just algebraic mishap. I don't know why that took so long, but hopefully the process is the most important. And the process is the most important, and the process is pretty straightforward. Just calculate the impedances. I'm going to keep moving on, so because that was already 17 minutes. If a periodic signal f of t with period
Oh, I have a
3,
question.
yes, yes.
It's just mainly about
Yeah, you can speak.
Oh, hello, can you hear me?
Yes, I can hear you.
Awesome. Hello, can you hear me now? Sorry, I'm so sorry.
Okay. Oh, okay.
Perfect. Now it's good. I was just asking when it is if it's a cosine because sometimes they give us a cosine wave in kilohertz, and other times they give us a sinusoidal. Is there any difference we do computation wise?
No. The only time you would consider the the cosine or sine of the input signal is when you're considering
Like a phasor?
yeah, when you need to use a phase like input output relationship phasors. Because the sine of any function, I'll just say t, the input phasor of this is this, because what I like to think of is if I have the easiest way to think about this is if I have a real imaginary, a plane, my sine of t starts at 0. And so it's very easy to just think of a sine wave as I have a arrow that rotates like this, or I have an arrow that rotates like this. So, and then what I'm looking at is the projection onto the real axis. And so the real part of this rotating arrow will start at 0, then go to 1, then go to 0 again, and then go to -1. And what is that? That is precisely a sine wave. Which is why when you're doing the phasors encode the where the how do you call it? Where the where your input signal starts. Whether it starts at 0, whether it starts at -1, 1, or wherever it starts. That is what the phasor encodes, and which is why if you're working with input-output relationship phasors, we want to kind of really consider the sine or cosine of the signal, but otherwise you don't really need to. This is mostly just an impedance question, which is why it's not important. Problem 3. If a periodic signal f of t with period 3 has exponential Fourier series coefficients, okay, then what is this? So my first initial reaction is just oh, this is just the integral over the period of this. And thankfully, we have something that directly relates the average power of a time signal and its Fourier series. There we go. Please correct me if I'm wrong, but I'm pretty sure this is right. And so all we need to do is we realize that, oh, this is just t times some of our Fourier series. And so what we obtain is that the integral from 0 to 3 of the time signal squared is equal to just 3 times the sum of the Fourier series, which is just 2 times 2 times 2 times 2, 2 times 2. So yeah, so we have 2 to the 5. Sorry, 2 to what? 2 to 2 plus 2 plus 2 plus 2 plus 2, which is actually clearly, oh, and then squared. Wait, that's clearly not right. Or is it? Hold on. Sorry. 11 times 2 to the 4. Actually, no, it is right. 2 to 2, which is there we go. Okay, yeah, because we have this because we want to consider the two values from -5 all the way to 5, which is 11 values. Which is why we do 11 times 2. Would the recording will be posted? Yes, the recording and the work will both be posted. Okay, which is exactly why we would do this and we get 132. Boom. Next question. Again, please feel free to ask questions please ask questions. What is the value of this integral? Well, directly from what we know about delta functions is that, actually, let me reorganize this function so that it's just easier to digest. We have t squared et t plus 1 and this delta function is located at 2, which clearly falls in between square root of 2 and square root of 5. Why? Because it's the square root of 4. Therefore, we can evaluate this function, and this is precisely just this function. Call this function f of t. Then our integral just evaluates to f of 2, which is equal to t squared, which is 4e squared over 3. Boom. Questions, comments, concerns? So you see that the exam is, well, just so far, like if this is your first time looking at the final exam, you realize that some of the questions are really just straightforward. As in, if you know how you do it, then it won't even take you a minute. And so you want to use this opportunity to kind of really focus on your fundamentals and get these easy problems through, so that on the hard problems you have a lot of time to think about. There will be harder problems.
Excuse me.
Yes.
I had a question regarding like test taking strategy. Like, would you recommend that we just like try and run through the whole test first and then like go back to the ones that we couldn't solve immediately?
There's no correct answer. Whatever works with you. What I did was, or if you really want to min-max, then I would run through the exam. Like if I look at it and if I don't know how to do it, I would just skip it. And then I will come back and I'll retake the question. I'll read all the questions that I skipped. That's basically how I would do it.
Okay.
Yeah. So, and most of the time, a third of the problems will be very easy. A third of the problems will be like okay, and third of the problems will be hard. It's like it's exact as the quizzes. It's exact same as the quizzes, the problem distribution. So, just being confident in the quizzes will be really helpful. All right. Suppose the signal x of t is cosine 4t and the input to the cascade is 3 LTI systems. What impulses shown below? Okay. It's kind of cheating that I know the answer already, but like my first initial reaction, even if I didn't know the answer choices, is I have a cosine function, which is just 2 delta functions, and I have 3 rect functions. So it's going to be it should be very clear that my output will either be a rect function, it will either just be a cosine function or 0, no matter what. Hopefully that's clear to everyone. It's because no matter what happens, let me actually show a general, I mean, it should be clear, but if I input any cosine function, if I shove a cosine function of any period into a rect function, a LTI system that is a rect function, that the frequency response is a rect function, then my output will either always, no matter what, be 0 or some constant let's say this is A rect, then it'll either just be A times cosine of AT. And the reason why it should be very clear is just that either the delta functions will fall into the rect function or it doesn't. That's it. And so let's draw this out. My cosine of 4t, this means that my cosine delta functions lie right here. And let's take a gander at the other ones. And like I will actually skip a lot of the work just by doing this. Examine h of 2t, which is, where is it? This is 3. You have this. And in fact, let me actually label that this is the frequency domain. And this is not sine of t, but is sinc. There we go. Then what is my Fourier transform of that? Was 3 times, off the top of my head, I believe it's 1 over, no, it should be 3 times 3 rect of omega over 6. Please correct me if I'm wrong, but I believe this is the correct Fourier transform. And we don't even really care about the constants here. We realize that this is a rect function that's only defined from -3 to 3. And observe that y of omega, so y of t is our output, right? But y of omega has a Fourier transform of y of t has a Fourier transform y of omega. And we know that by cascading, we could just kind of multiply all these together. By the commutative property of addition, sorry, multiplication, we can just rearrange the products and realize that this is just 0. Therefore, because this is 0 because our delta functions do not line up with h2 of omega. Therefore, we have that this product right here can just equal to 0. And so what we obtain is that the output signal is just 0. Let me fix my writing here. Should be pi over 3. Thank you. Yeah, some of these I kind of don't recall off the fly. Yeah, this should be pi in the front. Thank you. There we go. And so regardless, even if you get the constants wrong, the fact that the rect function doesn't align with the delta functions is probably the most important part that you need to know. Otherwise, pretty straightforward question. Let's go next. What is the inverse Fourier transform of the function shown below? So very immediately, my first gut reaction is, oh, this is delta, and this is a sine function, or it could be cosine. That's just the thing. Like it's as in like we have delta functions that are nicely spaced out from 0, which is very significant of a sinusoid, and we have a just delta function on its own, which is significant, which signifies that it's just going to be a constant. And so, first of all, let's work with number 1 here. Do I bracket these nicely? Number 1. We know that 1 has a Fourier transform of 2 pi delta omega. Therefore, 2 will have a Fourier transform of 4 by delta omega. Yay, we're done. Number 2. This part, I will work with, I'll factor out the negative, and I'll only work, actually, I'll factor out the 2 pi as well, or I'll factor out the 2. And I want to work with the following. Plus, all right. Oh, and also it's like this. So now the question from here is, how can I tell whether if it's cosine or sine? And the key signifier is to observe whether if it's a sum or a difference between the two delta functions. I completely omitted the delta. If it's a difference between the delta functions, then it will be a sine function because, well, sine is just e to the j omega, or I'll just say e to the, e to the j omega t minus e to the negative j omega t in the numerator. And like that's kind of the pattern matching thing that we need to see here, is that these delta functions, like the Fourier transform of sine and cosine could directly come from Euler's formula. And so if you see this parallel, it'll be very, very convenient for you to see that the Fourier transform of this will just be -2 times the Fourier transform of, let me just rewrite for elaborate. See, now the only issue is that if we recall, we know that our Fourier transform of sine of like AT has a weird constant, or like has a J factor in it, which is very undesirable in my opinion, because it clearly doesn't align with our question right now. Yep. So this is one thing that we know. But that's okay. And the question is, why is that? Well, what does this directly mean? Actually, maybe I don't want to draw it yet. What does this exactly mean? Well, I could just divide each side or multiply each side by negative j. It's just a constant. Remember, Fourier transform is a constant, so this is just a constant that we're multiplying. And we obtain exactly what we want. And so we do this exact trick, or not trick, but we do this exact thing onto the question right now at hand. And what do we obtain? We obtain that it's 2j. Hold on. Let's see if I'm missing out on anything. I am fine. We have -2 times negative j, so hold on. Yeah, I'm fine. The Fourier transform of that part is immediately negative j sine of 2 pi. T equal to 2j sine of t. I think I'm off by, I believe I'm off by a small factor here. Yeah, I'm off by a factor here. If I add those two, then it won't add up because I want a negative sign right there. Let's try to debug where I got my sign error. Let's see. Hold on. See where I got my j over there. Divide each side by, multiply each side by j. Get negative. Sorry, perhaps my Fourier transform is a little off. see. No, I believe it. I believe this is fine. Yeah, this is good. Divide by j or multiply by j on each side. Okay. Negative it. That's fine. Huh. I don't see where I'm. If I only cancel the j, it should be negative 1 over j. Da, 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 da. Hold on. Oh, I am a buffoon. Yeah, I just purely multiply by j. Then that should cancel it out. Oops. Yeah. Negative sign error. Sorry. And so we get negative. And so what we need is just 1 plus 2, or the Fourier transform is linear. So we have Fourier transform of 1 plus 2. Thank you for the corrections. Is equal to the Fourier transform of some of those. Then we just get it's 2 times this, which is exactly what we want. Voila. And that's our answer. Thank you for your algebra assistance. Next question. If f of omega is the Fourier transform of the piecewise linear function f of t below, then what is f of 0? Very classic question here. I just want to be clear, very clear here, that if you take 0 to be your Fourier transform coefficient, then this just goes to 1. And so let's just find this area. Well, realize that this area cancels out with this area. And so all we need to worry about is kind of this area, which is exactly just 1. Voila. Perhaps I want to put everything as blue. And so the trapezoidal areas cancel out. And so all we have left is this blue section. Let me do it in purple or something. This cancels out with this. And so all we need to worry about is the kind of the unit square that we have over there. And so all we need to worry about is the unit square, yeah. And then so the area over the entire curve is just 1. Next question. An LJ system with impulse response h of t produces an output y of t when the input x of t is applied. What would be the output if an input of that will be applied to a system whose impulse response is that? This is the time shifting property of convolutions. And so basically what this is that if we have as an example, if we have a of t convolved with b of t equal to c of t, then if I apply any delay to one of the signals, then the output is also delayed or pushed, delayed or pulled early, or whatever. And so this particular question, we observe that if x of t is convolved with h of t in order to obtain y of t, then x of t convolved, x of t minus 3 tau convolved with h of t minus 5 tau is equal to Well, we can do two things here. What I'll do is I'll just move all of the delays onto one side. Actually, we just delayed. I don't know how I want to model this. Like, I hope my intuition is very clear to everyone. I just want to see how I could algebraically make this very clear. Okay. Let's do this. Let's say this is equal to some mystery function, I don't know, like z of t. Then, what is it? Then this would be equal to z of t, yeah, z of t. So I undelated it. I made plus 3 tau here. Hence, I must do plus 3 tau over here. You can do, yeah. Like, I understand that. I could just delay it both, but sure. I could just write it like that. Like, I understand that I could do that. That's just maybe there was another coherent way to write it, but perhaps it will just be better for everyone to just absorb it like this. And so I will. And this will be just equal to. Essentially, you could like delay it twice. And of course, this applies to cascading, where if you have minus tau naught, minus t naught, minus t1, and minus t3, t2, then you could add these all together. So like the delaying, you could kind of transfer it down a cascading system. And so we just get this answer. Not too bad. I just hope that this kind of intuition kind of falls through. If a linear time invariant system has frequency response of h of omega equal to that, okay, then what is the output at time t equals -1 if the input is x of t equals to 3? What in the world? Okay. So this question is reliant upon the idea where there's multiple things actually. Like it is multiple things. You can do it in two different ways. One is to interpret it in the way where complex exponentials are eigenfunctions of LTI systems. So intuition one, so like your method one is e to the j omega t is eigenfunction. Or your second way of interpreting it is just to do just brute force Fourier transforms. Both methods work. One method is significantly easier than the other. And so what I want to say here is that if I input x of t, if I input 3 e to the 4jt into a LTI system, then observe that this has omega equal to 4. And so my output will literally just be h of 4 e to the 4jt. The Fourier transform way follows the same exact way, where you convert this into delta function, and the math is exactly the same. Because I don't want to do that math, I'll do it the eigenfunction way. And so what we obtain is that our output, this is our output signal, and now all we want to do is obtain y of -1. So it's 3 times h of 4, which is 4 times e to the j 4 plus pi over 2. Doesn't look too fun. And then times e to the 4j -1. Hopefully I'm not wrong there. And so we have -12, we have 12, we have 4j That is odd. Oh, actually, hold on. Maybe I don't want to do that. I'll do e to the 8 plus pi over 2. That still doesn't look too fun, but that's okay. Times e to the, oh wait, actually, never mind. I want to do that. I do want to do that. 4j plus pi over 2j minus 4j. And look at that. Oh, okay, sure, I'll show it the Fourier way. This is method 1. And so we see that these exponentials cancel out. So it's just e times, well, we say goodbye to these two. And all we have left, conveniently, is e pi over 2j, which is equal to just 12j. So our answer is correct. Now, let's just try the other way. By the Fourier transform way, we know that the Fourier transform of x of t wait, I forgot what it was. It's 3 4 jt. The Fourier transform of this is 3 omega. Hold on. It's 2 pi. 2 pi omega of omega minus 4. Omega times 4. Omega minus 4, yeah. Yes. And so now we know that the output signal will admit a Fourier transform, y of omega, which is equal to x of omega times h of omega, which is 6 pi. I'll just leave it at 3 and 2 pi. Delta omega minus 4 and h of omega. Well, what do we know about products with delta functions? We know that it's going to be the product of a delta function and another function is precisely just another delta function located at the same exact point, but you are multiplying by the value of wherever this delta function was evaluated. And so it's just h of 4. And crazy enough, let's take the inverse Fourier transform. This is a constant. And so what you have is 3 h of 4 as constants. And then you have the inverse Fourier transform of 2 pi, the same exact thing. And so if you take the inverse Fourier transform of this, sorry, this is just a rearrangement. You get the constants outside, and this inside part is the exact same thing. And we observe that it's the same exact algebra as what we saw above. There we go. It's the same exact algebra as what we saw above. And the algebra follows. So like the approach is the algebra is the same. The approach can be different, but both approaches will be the exact same, will yield the same answer. Hopefully that answered your question. Next question. The piecewise linear signals x of t is shown below. What is x of 0, where x of omega is the Fourier transform of x of t? So this one you use, okay, well, it's called the Fourier transform version of Parseval's, but I believe it's called Plancherel in like mathematical terms. I believe it's called Plancherel. It's the same exact thing where we know that the total energy of a signal is equal to, please correct me if I'm wrong, but I believe it is 1 over 2 pi of the same exact, not same exact, but the integral of the Fourier transform squared. And so, wait, what am I thinking of? Wait, sorry. Wrong one. I'm thinking of the exact wrong one. X of 0 is just precisely, what am I thinking? X of t, e to the j omega t, but omega is just 0. And so we know that this part just goes to 0, or just this part just goes to 1. And so we have this. And all we need to do is just take the area of x of t. And so we realize that it's just 1 unit square, 2 unit squares, 3 unit squares, 4 unit squares, and 5 units, or a triangle with area 1. 1, 1, 1, 1, 1. The area is 5. Sorry, I don't know what in the world I was thinking. With like the part. Don't ask. I relooked at the question again. And I was like, wait a minute, I don't need to do any of that area stuff or the parcel stuff. So yeah, this is a very straightforward question as well. Number 11, the output of an LTI system is as follows. When the input is a unit step function u of t, what is the impulse response of the system? What a great question. Well, my initial gut reaction is, okay, well, let's actually just draw it out first. Where to start? Well, the Fourier transform of u of t is, what was it? I believe it's just 1 over j omega, if I'm not wrong. Yeah, it should be just 1 over j omega. And why is this true? Well, you could actually just solve for it by just directly solving for you could either solve or have it written down. The math is very straightforward. All you need to do is take an infinite integral. Because if you take the Fourier transform integral, then what this function does is it basically just kills the entire bound from 0 to infinity. And so you could just solve for this. And so what we see is that I inputted this and I got that out. Well, if I let this be equal to y of t to be my output, then clearly y of omega is a bunch of delta functions. And please can finish yourself this. If I have a sum of sinusoids, a sum of cosines and sines, hell, if it's even just like a sum of, if it's a periodic function, clearly this is a periodic function. Periodic functions have a Fourier transform that are a sum of delta functions. And so essentially what I'm thinking here is, well, let's actually just write it out first. Well, this is actually a well-made question now that I think about it. This is 5 pi, let me factor out the pi, delta of omega minus 3 plus omega plus 3 plus 8 pi over j omega. Wait, is this Did I write it wrong? No, I didn't. Omega minus 3 plus minus omega plus 3. And so I could actually simplify this. Let me actually zoom in because I want to write more precisely. I could kind of simplify this because I have delta functions that are kind of it's the same delta function. And so what I obtain is that it's actually a sum of two delta functions. So let me draw a line there so to kind of isolate. I get 5 pi plus, never mind, I'll leave it like this actually. I'll leave it like this because I don't want to make the algebra any harder. And I know that y of omega is equal to x of omega times h of omega. So let's actually write that out. Even though I don't want to. My God, that's a lot of writing. I'll just copy paste it. I do not want to add text. Hello. There we go. Voila. This is equal to some function x of omega times h of omega. All right. So let's see here. Remember, h of omega is actually just a function that we know. Sorry, x of omega is something that we know. It's actually 1 over j of omega. And so all we need to do is find this and find h of t. That's our goal. Well, let's just multiply each side, but I think we can just multiply each side by omega j, and then we can find out what our answer is. So we realize that our answer, h of omega, is quite literally just 5 pi omega j delta minus 3 plus 5 pi omega j plus 3 plus 8 pi omega, and then we just keep going, 8 pi omega. We have this. You don't necessarily need to expand out everything. It's just that like it's kind of important to see, like, of course there's a shortcut. It just takes a little while because I'm writing out everything, but there are shortcuts to this question, and I assure you. Let me write out everything first and maybe give a few things that I see. Let's finish the question first anyway. And so we observe that this is just equal to, hold on. I do not want to do that yet. Hold on. Multiply by j omega. That's good. That's fine. J, good. Okay. And then we also realize that we're evaluating this function at like, we're multiplying this. This is a function of omega, and we're multiplying it by a delta function. And so remember what we know about how multiplication works with delta functions is that it takes the exact value at that point. So this is at omega goes 3, omega goes -3. This is omega equals 3 again, omega equals -3 again. And so we evaluate a little longer. My goodness gracious. J, I'm just gonna write delta 3. You know, you could always make it like it's a delta placed at 3. So I'm just gonna abbreviate it just because it is coherent to me. This will help you save time. -j. In fact, maybe I won't do that yet. Oh yeah, this is -3, and then delta at -3 plus 24 pi omega 3 at delta at 3 minus, sorry, plus 24 pi at delta negative 3. I'm trying to see if I have any questions in the chat so far. Okay. And so for this point, what I'll do is I will, it's so much algebra, but I will factor out a negative here, and I'll make this first part all negative, so it'd be 15, sorry, it'll be 15, negative 15 pi over j delta 3 minus pi over j negative 3 plus, this one should be a little easier, it's just 24 times pi delta 3 plus pi delta negative 3. And taking the inverse transform of this, then this means that h of t should be fairly easy. You just use our known Fourier pairs, negative 15. And then this yields us sine of sine of 3t. Next one gives us cosine of 3t. And what do you know? That's exactly our answer. So yes, it is true that this question was algebra heavy and it took us actually like, I don't know, like maybe almost 10 minutes. But remember, okay, so let's actually kind of do like a time breakdown, right? I look at this question, I'm like, okay, I realize first I know this, like my first initial gut reaction is to see, oh, I want to analyze this in the frequency domain. Then I realized that x of omega is actually very easy to solve. We get it almost immediately, either because from like writing it down or just solving for it. Then you realize that you could actually move x of omega to just the other side. And so now we just obtain this big block of delta functions. And we're like, oh, now we just need to kind of like use my delta function properties and figure out what this is organized to. And I assure you that will take maximum 4 minutes. If you can save yourself from writing and keep note of which delta functions go where, then I believe it will be significantly easier. But yeah, that's definitely not the easiest question indeed. Just because like look at all that writing we have to do. But all the thought is there. All the thought process still remains clear, as in you want to make sure to know where to analyze your function from looking at the question. Again, if you have any questions, please feel free to ask, and I'll be happy to answer everything. But otherwise, I'm gonna keep going. We're right on pace to finish in 3 hours. Which one of the statements is below is true? The function x
Oh,
of
I
t.
have a question about approaching the last one.
Yes.
Just really quickly, I did approach it a different way. I thought it was a tiny bit simpler, but I just wanted to run it by you, like in case it just worked for this scenario and it might not work for other ones. So I did use the Fourier transfer equation where I believe I have the unit step function and I put it in terms of tau. So I kind of use the tau equation. So it's the integral of negative infinity to infinity, the unit step function, and inside of it, it's going to be t minus tau. And then after that, I multiplied it by the impulse response, which is h of tau, d tau. And I set that equal to my output, which is the 5 cosine 3t. And then after that, I just used it. I kind of like took advantage of that. And then I kind of set the bounds of the unit function. If you kind of catch on, because it's t minus tau. So I moved the tau over. So I was able to set the bounds to be negative infinity to t, and then h of tau, and then d tau. And then the other side is still equal to our I believe our y, our output. And then after that, I got the derivative of it. Yeah, that would be d tau, and then the bottom bound would be negative infinity. And then that would be 5. Yeah, perfect. And then I did the derivative.
Oh.
Yeah.
You can do that too.
That would work. Okay, perfect.
Yeah,
Yeah.
that would work.
Yeah, I just did the derivative and then yeah, it worked out perfectly.
That's actually probably smarter. Maybe I should have done that way. That's also actually a way to do it. Let me actually write that down. Well, this method actually is not that bad either, but they probably what you did was also pretty smart.
Awesome, cool. Yeah, I just wanted to. I like the algebraic one too because it helps me understand. But yeah, I just wanted to do both.
Let me write that down. That's fine. I get e to the. Oh, okay. For that, you're missing a part where it's if I take the integral, then I get -1 over j omega e to the negative j omega t. And then imagine taking the limit. This is something that's spinning. And then this is something that goes to 0. Imagine the magnitude of this. To solve for this, consider the magnitude of this as t goes to infinity. And then this will just be equal to 0. Which is why you get exactly what you want. Next question. Which of the statements below is true? The function x of t, which is the sum of sines, has exponential Fourier series where that is true, but the issue is that x of t is not periodic. And so it's none of these. That's it. Why? It's because this has period 2 pi over 3, and this has period 2, and there exists, and the ratio between the two periods, so let's say this is T1 and T2, T1, T1. And the ratio is irrational. Therefore, it's not periodic, and we're done. Next question. The input signal SFT is below 2 multipliers. What is the Fourier transform of y omega in terms of the output signal y of t? Okay. So you can do this 2 different ways again. I will do it one way. The other way follows similarly. Essentially, what I want to do is I realize that, okay, this is equal to, or not equal to, but the Fourier transform of this is x of omega is equal to convolved, well, convolved with of a bunch of delta functions. Oh, I really don't like writing out deltas. It's so many parentheses. I'm sorry. I'll just write out like this. Hold on. Pi delta 3 plus pi. Oh my God, so many parentheses. Oh my God. Okay. Parentheses, small parentheses. This convolved with this. There we go. And recall, well, I'm gonna leave this right here, x omega. And remember, we could treat delta functions like polynomials. I mean, in a certain sense, they're basically polynomials. And so please refer to discussion, I think it's discussion 7 or 6, where I discussed about multiplying convolving delta functions very quickly. But what we can do is first we could use bilinearity of the convolution and pull out both of the all the pi's. So we get pi over 2, and we only get the delta functions left. Voila. This is equals, not that. And now we can pull this out again. So we get 1/4. And then we actually can start convolving stuff. So we could convolve the inside things, and we obtain delta 6 plus 2 delta 0 plus delta -6. Very, very it's extremely easy to kind of work with this stuff. Like remember, this is basically like polynomials where I'm doing x to 3 plus x to -3, and I'm multiplying it by x to 3, x to -3. Where we see parallels. Where if I just do this, multiplying polynomials, I kind of just combine the coefficients. And I get, oh, it's x to 6, and I get 2 at x, or I just get 2 at like, because I combine these two, I do the FOIL, and I get 1 for the last one, which is exactly the same here. I get 1 at 6, I get 2 at 0, x to 0, and I get 1 at -6. And so getting used to these kinds of delta function convolutions will be very, 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 very helpful. Anyways, now I just want to finish it off by realizing that, oh, I'm convolving a function with a bunch of deltas. And so there's just x of omega plus -6 plus 2x omega. It's just 2x omega. And then x omega plus 6. Voila. And so it is clearly this one because we have, well, okay, maybe I want to kind of factor out the coefficients, and so I'll just do this. I have 1 in the middle that is of height 1/2, and it's like the same exact shape. And I have 2 pinpointed at 6 and -6, each with the half of the height, which is why it is very nice to know how to convolve delta functions very quickly. Because if you knew that how to do that, then this problem will take maximum like 2 minutes. Like, oh, I have x omega, and I'm clearly placing copies of it. All I need to know is where these copies are and did I scale them up. And well, scaling them up is just by using the bilinearity of a convolution where you pull out constants from each term. And furthermore, you could see how many copies you place and where you place them by considering the convolution of the delta functions where they're naked, we don't have any constants in front of them. And this will be very, very helpful in the long run. Otherwise, you get our desired answer. Figure A, there we go. Anyways, if there's no questions, I'll go move on to the next question. Remember, if you have any questions, please feel free to let me know. What is the Fourier transform of the piecewise constant function f of t shown below? This question, I want to clearly see that it's just a rect function plus another rect function. And so it suffices to figure out what is the Fourier transform of each. And so I initially start with rect of t over 4. Hopefully this is clear. And then this has a Fourier transform of just 4 sinc of omega, I believe it's omega t naught, omega t naught over 2. So it should be 4 omega over 2. Again, maybe I'll write it out because I want everyone to know. Rect of t over 2, or maybe I want to write this. This has the Fourier transform of t naught or 2t naught sinc of omega t naught. And so maybe if I could just, 4 and 2t, 2 omega. And then the blue function is clearly 2 rect of t over 2 because it's width 1. Oh, it's width 2. Wait. Yeah, okay. Sorry. I confused myself for a moment. And we obtained that this is just 2 times sinc of omega. Clearly I'm missing something here. 2t, yada, yada, yada. Yeah, that should be right. The Fourier transform of the piecewise constant function. Boom, boom, 2t. Oh, sorry. Yeah, it should be 2 times 2 sinc t. Should be 4. There we go. And so take the sum and we obtain our desired answer. I think someone said, yeah, thank you. Thank you, Mo. So this is, remember, we initially had a 2 constant up here, so we have to take 2 again, and then we multiply the whatever the width was. And so we obtain our desired answer. Suppose y of t is the output of an LTI system with impulse response. H of t, okay, it's just 2 delta functions, should be a signal here. When x of t is equal to that. What is, okay, so clearly, again, this is a delta function convolution question, and this will be hopefully very easy. We know that y of t is equal to x of t convolved with h of t. And in fact, I will write it out. It's delta negative 2. Remember, I like to put whatever is here of considering where it is placed. This is delta at 0, delta at 3, convolved with delta at negative 1, and delta at 2. Remember, and well, maybe let's just solve for everything first. And let's consider the batch of delta functions. Boom. And that's it. I'm done. Like I just convolved 3 delta functions with a sum of 2 delta functions. Just like that, under like 20 seconds. That's the power of the polynomial interpretation of delta functions. So please consider kind of like building a strong foundation of with regards to like using that kind of method. And so we realize that we're integrating the delta functions from -2 to 3. Which ones fall in -2 to 3? Well, this one does, this one does, this one does, this one does. Only 4 fall into that, so we just get answers 4. Okay, next question. If x of t is equal to f of t plus f of t of minus 4 plus f of t plus 4, and the Fourier transform of f of t is f omega, then which of the following is the Fourier transform of x of t? Great question. Well, we know, I'm going to list down the properties, and then we're going to do the question. We know that any function translated, let me do an arbitrary function, any, like, I need a good letter. I'm sorry, I'm trying to find a good letter. G of t. Let's say g minus t naught. T minus t naught will have the Fourier transform. Okay, sorry. If g of t has a Fourier transform g of omega, then g of t minus t naught will have a Fourier transform of g omega times e to the j omega t naught. Or perhaps it's negative. Let me check my intuition. Yeah, it should be negative here. That looks right. Yes, good. There we go. And so, okay, there we go. It's whatever. And so if I take the Fourier transform of x of t, remember, by linearity, it's actually just the Fourier transform of f of t minus 4 plus the Fourier transform of f of t plus 4. And these two are actually very evident. It's just f of omega times e to the negative 4j omega and f of omega times e to the negative 4j omega. What in the world? I wrote two of them. It's plus j 4j omega. Wait. Yeah. And well, what do you know? This, we could factor out f of omega here, and we get a sum of conjugate complex exponentials. And well, what do you know about what is it? Conjugate complex exponentials? Well, this is just cosine. 2 cosine of 4j4 omega. We obtain our answer. Boom. Not too bad. Not too bad. '17. Suppose x of t is a periodic function with an exponential Fourier series as follows, where we're given that determine the value of x of t when t equals negative 12. T equals 12. So first, I want to analyze x of t. I'll be completely honest. I looked at this question. I'm like, oh, how do I do this? So I'm gonna take it step by step. This is a very good opportunity to see how to map out your thought process, especially when you solve this kind of problem. And so I want to look at x of t and see what is its period. I want to get as much information as possible. Well, we know that the Fourier series comes in the form x of n e to the j k omega naught n t. This means that, no, I add an extra constant, sorry. This means that omega naught is equal to pi over 2. This means that the period is equal to, or however how it works, should be 4. Okay. First moment of observation is that our period is 4. So if I want to determine the value of x of t at t equals 12, it's kind of the exact same as evaluating x of t at t equals 0. Is that clear to everyone? So remember that since we have this kind of nice relationship. Okay? And so, what is this? This is equal to n in z of xn e to the, wait, if t equals 0, then that entire top exponential just goes to 0. That's just 1. What does this tell us? The value of x, the function x at 12, at t equals 12, is just simply the sum of all of the Fourier coefficients. Isn't that nice? And so this actually should be very easy to solve. we're just doing sum of 1 plus 1/3 plus 1/9 dot dot dot. Clearly, this is a geometric series, and so this should be the sum is equal to 1 over 1 minus 1/3, but that's our ratio, and thus we obtain. Well, maybe I want to do this. That's a little better. And so this is just 3/2. Voila. That's how you would do, or that's how I would do this kind of question. 18. Let f of t be a periodic function with period 3 pi. And suppose a non-zero exponential function, non-zero exponential Fourier series coefficients, fn, are as shown below. What is, oh, well, that's not that bad. Where would I start? Oh, well, recall that we want to, if we f of t is equal to this, then recall that f of t will have a Fourier transform of, okay, I need to get this right, but it should just be 2 pi, the Fourier coefficient times the sum, 2 pi times the sum of fn delta function at this. Hopefully that is consistent with everyone. And this kind of relationship is directly adopted from the Fourier series. And so now we can immediately deduce that the Fourier transform, or this is our Fourier transform, this is equal to 2 pi times, and we have enough delta, you have deltas to the point where like it's very easy to evaluate. And omega naught is equal to 2 pi over 3 pi, which is equal to 2 over 3. And so this is delta of, I'll just do this plus 2 times delta at this, and then plus 4 times delta at this. And that's equal to f of omega. And remember, we're evaluating the integral from 0 to 2 of f of omega, which is a sum of delta functions. And so this integral should actually be very easy to evaluate. And so what falls into 0 to 2, well, we have this, oh wait, we have all three. Actually, no, we shouldn't have all three. We only have two. We have this and this. It falls into the integral of area of the interval of the interval of integration. Sorry, and so since we have these two delta functions that fall into the interval of integration, we only integrate over those two delta functions, and so it's integral from 0 to 2, or more so, it's just 2 pi times. Yeah, I'll just write it out. To and thus, and then don't forget 2 pi. 2 pi times 6, which is equal to 12 pi. Voila. All right, we are halfway through the final exam. And it's been 1:30, so not too bad. We're right on track. Let's keep going. Ooh. Suppose y of t is the output of an LTI system with the impulse response shown below. Oh, okay. When x of t is the input. If y of 3 is equal to 1, then what of which of the following could be x of t? Damn, good question. I had to think about this. Hold on. Okay, so my first observation is that h of t is actually just a rect function. If I could draw it out, then I mean, I will draw it out. It goes up by 1, and it falls at -2. No, sorry, falls at 2. There we go. And now I want to convolve. We understand that x of t, in the time domain, we have this kind of input-output relationship, where I convolve this with this, and I get y of t. Okay. And I also have information about y of 3. Oh, then this means that, let's actually think about this. I want to make this as easy as possible for me. I know that y of t is equal to the integral from -infinity to infinity for, I'll leave x of t, and I'll bring in h of t minus tau. I believe, I think this is the nicer way. If it doesn't work out, I'll flip it back. Okay, and then I observe that y of 3 is specifically when I do this, and I will actually draw out h of 3 tau. This would be something that looks like this. Yeah, there we go. This would be h of 3 minus tau. This 3, this 1. And so now that we know that h of 3 minus tau is just a rect function from 1 to 3, this integral is extremely simplified. It's just x of t integrated from 1 to 3. And this equals to 1. And so all we need to do is find a function such that if you integrate from 1 to 3, it's equal to 1. And given how Ziegler quizzes operate, there will only exactly be one answer choice where this will work, or none of them. And so let's observe all these answer choices. I'll tell you why each one is not. And so this one kind of depends on how you understand unit step functions and how they behave. Clearly, every single one of these answer choices is a difference of unit step functions. And so it suffices to kind of understand the ins and outs of how you can perceive an input in like these kinds of combinations of unit step functions. And so let's actually label each one. This one goes up. So how I like to think about it is I like to think about when it goes up and when it goes down. So I'm adding, so unit step function, it goes up, and then at some point it goes down. These two numbers define when it goes up and when it goes down. And so these are all rectangles. Starting at a certain number, ending at a certain number, and height of a certain number, just from observation of each of their respective formats. And so clearly their height is very self-explanatory. It's just exactly the number that precedes it. And now we just need to know when it starts and ends. This one starts at 1, ends at 3. This one starts at 1, ends at 3. This one also starts at 1 and ends at 3. This one starts at -3, ends at 1. -3 ends at 1. -3 ends at 1. Now I want to ask you, which function will give me an area of 1 when I integrate it from 1 to 3? That should only be one answer, which is the rectangle of width 2 defined between 1 to 3 and height 1/2, which is exactly how we obtain our answer. So in reality, this may seem like wait a minute, I have to check every single one. Yes and no. If you know how each graph intuitively will look like, then no, you don't have to check anything. All you just need to know is when it starts, when it ends, and doesn't match the integral. And that's it. But if you do not know this, then you'll have to check every single answer choice until you get the right answer, which is why it's just inconvenient. And so knowing how unit step functions operate will be very helpful. Number 20. The input voltage x of t and the output voltage y of t of a circuit in sinusoidal steady state satisfy this following. Which of the impulse responses is a system at xt equals 1? I believe there was a question exactly like this on a previous quiz. The way you approach this is as follows. You take the Fourier transform of those sides. And then you see that this is 2 y of omega 4 x of omega minus, okay, I believe it is this. Then we have this. Then we have that the frequency response is 4 over 1 plus 2 plus j omega. This means this has a Fourier transform, inverse Fourier transform, that is e to the negative 4 e to the negative 2t ut. And so if h of 1 would be 4 e to the negative 2, that's our answer. Voila. How do you know the transform of the derivative? Good question. We have the following property where the derivative has a Fourier transform of negative j omega f omega. Given this Fourier transform property. To derive this, essentially what you do is you just push in the derivative operator into the integral, and then you obtain this, and then you pull out a constant. What would the second derivative be? Well, you'll pull it out again. And so you take the derivative again. I'll just do it in general, actually. dn dt to the power of n. This is just negative j omega n f omega. As long as f of t is n times differentiable, then yes, this will hold. Okay, actually, yeah. If x of t is sinc of 3t, then s and s of t is is an impulse train. Oh, what do you know? It's a sampling problem. And y of t is, okay. What is a Fourier transform of y at omega equals 2? Good question. Well, let's think about this. Okay, for me, I kind of like wrote it down, but it's actually completely fine. X of t has a Fourier transform. Actually, maybe I'll write it here. This has a Fourier transform, x omega, which is equal to pi over 3 sinc rect of omega over 6. This has a Fourier transform s omega, which is clearly you see that omega naught. This is 2 pi for 3n. So omega naught is just be j omega naught, negative j omega naught. No. I believe not. Or is it? Hold on. Hold on. Actually, I think that is right. It should be normal j omega. It should be, yeah, it should be normal. Wait, I made an entire typo over there. What in the world? So yeah, all the algebra here is fine. It's just should be negative over here. It should be negative over here. Yeah, yeah. Sorry. Thank you for the catch. Yeah, it should be just j omega. I had a extra negative right there. Thank you. Anyways, back to this question. And so the impulse train will have a Fourier transform of, if I recall correctly, it should be just omega naught, which is 2 pi over 3 times the impulse train at no, sorry. This is the period. So t is equal to 2 pi over 3. This means that omega is equal to 3. And so this would be 3 times 3, and then spaced out by 3n, and then z. Yes, okay, perfect, thank you. Yeah, I just caught that. Perfect. And where does this come from? Well, maybe it's important to elaborate that for any impulse train, it has the Fourier transform of omega naught impulse train where of course omega naught is equal to 2 pi over t. So, that's just something important. And so we obtained this kind of result. And now I want to do y of omega is equal to 1/2 x of omega convolved with s of omega. And what is this? This is, I guess I could pull out a bunch of constants. It'll be 1/2, or maybe I'll just write it out. Negative 1 over 2 pi of pi over 3 rect of omega over 6 plus, convolved with 3 times an impulse train spaced out by 3. I could pull out a bunch of stuff and obtain the fact that it's 1/2 times a bunch of copies of rect functions. So and usually at this point, it's not, I mean, you can kind of like write it out. Like nothing's stopping you. I like to just draw it out because drawing out impulse, like copy impulse train convolutions is probably the easiest thing. And so essentially what I have is, in fact, I'll actually just leave it in a form where it's easy to see. I have rect functions of length 6 that are placed 3 apart. And so I will actually just draw some out. That's 1. That's one anchored at 0. That's one anchored at 3. Do another hot color. Anchored at -3. So on and so forth, whatever. And we realize that at 1, or sorry, at 2, we have it's a sum of 2 rect functions. And so if we add all these together, then this actually just becomes, sorry, this height should be 1/2. This is our resulting function if we add it all up. And so what we obtain is as just 1. You could do it both ways, but like algebraically, it'll also work out. But again, it'll just be easier to draw it out and realize that I'm adding a red one and a black one at that point, precisely. Okay, next question. Problem 22. Consider the following sinusoidal steady state circuit with voltage source f of t. If L equals 2 and C equals 4, then what is the value of the voltage V of t when that? And so I don't know if I have mentioned this before, but specifically for RLC circuits, we have that, how do I put it? Here, let me actually just do it first and then observe, maybe show it or prove it if people are interested. But in general, for RLC circuits, let's obtain our thing first. So clearly, by superposition, we have 2 things. We have omega 1 is equal to 1 over 4. And this one has omega equals 2. And so it kind of suffices to find the transfer function for each individual output. And so what I want to see is, like, your initial gut reaction should be something like this. I want to say that the output voltage is 2 times the transfer function evaluated at 1/4 plus 4 cosine, 4 times the transfer function of 2 cosine of 2t. And so let's get right into this. All we need to do is solve for h of omega, which is clearly just a voltage divider. And so let's actually just solve for that. We have h of omega is equal to 1 over j omega c divided by 1 over j omega c plus j omega L. Thus, we obtain that this is just 1 over 1 plus 1 minus omega squared CL. And so, what is this? L is that and that. Then they get 1 over 1 minus 6 omega squared. It's not 6, it's 8. I don't know what's up with me today. And so now all we need to do is just solve for VT. VT is equal to 2 times, what is h of 1/4? It's just 1 over 1 minus 1/2 cosine of whatever that is, 4 times h of 2, which is 1 over 1 minus 16, no, 1 minus 32, and then whatever we had up there. And so now what we obtain is this is 4 times cosine of 1/4 t plus minus 4 over 31 cosine of 2t. Voila, and there's your answer. So again, another straightforward question, just mostly using circuits. Let me check. Again, if you have any questions, please feel free to let me know. I'll be happy to go back to the question as well, if anyone needs to. But yeah, otherwise I'm just powering through this. Whew. Problem 23. Which of the following is true about the integral shown below? All right. So just off first glance, I see a t minus tau and I see a tau and we're integrating by tau. This is clearly a convolution. So this is just a convolution between cosine of 6t convolved with sinc of 5t. And immediately, this should just tell me that I have a rect function. This is some constant c. Like at this point, right? You don't even really need to care about what constant goes there. All you need to know is that it ranges from some value to some value. And this is a rect function anchored at 0, obviously. But it's going to be of width 10. And this is 2 delta functions. And so let's actually just draw it out. Cosine 6t is just 2 delta functions, happily sitting at 6 and -6. And we're convolving it with we're multiplying it to the following function's frequency response. So this is all in omega, right? This yields so consider that this will have, let this equal to y of t, then y of omega is equal to obviously the product between, okay, let me write this out. I'll just say this is I need 2 nice letters, r of t and this is s of t. Oh, that's for sampling though. I'll do p of t and q of t. Then y of omega is equal to p of omega and q of omega, which is quite literally just equal to 0. And therefore, y of t is equal to 0. Boom. And then we're done. So mostly this is just an observation question where you have to realize that t minus tau really screams at you that it's a convolution. Next question. Problem 24. What is the impulse response of an LTI system whose relationship between input x of t and output y of t is given by the following function? And hey, wait a minute. Isn't this just another convolution? Very funny. In fact, what's even funnier is that the bounds are different. So how would we think about this question? What a shame. How do we think about this question? Well, if you've seen enough of these questions, then you would know that a unit step function kills off a part half, I want to say half, but a certain section of an integral's interval. And so what your first argument can really help you out with is that if you rearrange this integral into integrating from negative infinity to infinity for u of t minus tau. The moment this t minus tau goes in here, you're integrating from negative infinity to tau t anyway. And then x of tau, d tau. And after this, you're basically done, right? This, you could change this to negative t minus tau. And now this is just a convolution between e to the negative t ut convolved with x of t. Oh, and boom, we literally just found our h of t. Voila. Magic. Or not magic, but like this kind of argument is very, very contrived. As in like it's requires you for you to be observant regarding a lot of these patterns where you see that if the interval of integration can be killed, it's most likely that there's a function, a nice well-defined function that you could kind of change it to in order to make it a general interval of integration and then rearrange it to something that's very nice. So most of the time, again, it's rearranges to something very nice, and then you apply what you know about this class. So this rearrangement thing is actually very, very important.
Can
Number
you
25.
Oh,
Yes.
Can you explain again how you changed the bounds of the exponent of the e, and then how I guess you changed the bound from the top integrand bound from infinity to t?
Oh, okay. Well, u of t minus tau is equal to a function that is 1 for all tau less than t, and it's 0 for all tau greater than t. It doesn't matter really what we define in the middle, because it doesn't really matter. Actually, I'll just define it just because why not? And if we could, and this exact y of t is equal to this, because if we're integrating from negative infinity to infinity, and we have this little unit step function in there, then it's doing the same as integrating from negative infinity to t. It's doing the same thing, which is why we could convert it into this kind of fashion. And then, of course, I rearranged just the exponent of e to the power of tau minus t. I just rearranged it I pulled out a negative, and I realized that now it's just a convolution between two functions.
Got it. And then for the u of t, you can just add the step function of u of t of minus tau just to kind of get it to cancel out
Exactly.
because it's just one, right? Is that the logic behind it?
Exactly. So it's just 1 when in these bounds.
Got it.
And then 0 for, so because it is 1 in these bounds, and it's 0 in these bounds, you can have that this specific function, this specific integral is equal to the same as this integral for all values of t. Is that clear?
Got it. Yeah. Thank you so much.
Perfect. All right, problem 25. We're very ahead of schedule. This is good. If x of t, I see. I got a comment saying that we should, well, it really depends, but we should do something like this. In most of industry, we use the heavy side step function where it's 1 defined at the it's equal to 1 at the jump, but it really doesn't matter. Like in this class, there will be no question where we'll ask you to kind of evaluate a value at like this corner, because that would be evil. Otherwise, it'll be very clear in the interval. We'll very clearly say, oh, we have a rect function that's defined like this, and I want you to multiply this rect function by an impulse placed at the corner. that's a little evil in my opinion, then in this specific scenario, we're very clear of what the value of this function is at 5, and so we need to take it. But whenever we make it very unclear, of like it's just a rect function, then we'll never tell you to find the value at this corner because it's just ambiguous. And so you do not need to worry at all about these little ambiguities. Yeah, just please don't worry about these ambiguities at all. But yeah, I got a comment on that. So yeah. If x of t is cosine of 2t plus cosine of 3t, is the input to an LTI system with frequency response as follows, then what is the output? And so this is very convenient. And so we know that we could do two different kind of scenarios for this one, and both scenarios are the same. You can either do a eigenfunction approach or eigenfunction intuition or a just Fourier transform brute forcing. I'll do the eigenfunction method because the Fourier transform method is actually very, very intuitive. As in, you just take the Fourier transform and just multiply it. And so we realize that x of t is actually just a sum of eigenfunctions and then this means that our output y of t by the eigenfunction property y of t is equal to 1/2 h of 2 e to the 2jt plus I will factor out the 1/2 because my hand's starting to hurt. I don't want to write 1/2 three more times. H of 2 e to the 2jt plus h of negative 2 e to the negative 2jt plus h of 3 e to the 3jt plus h of negative 3 e to the negative 3jt. Okay? And we realize that h of omega is actually just 0 at some point, straight up. And we can just kill these two. What we have left is that these are just ones, so we could kind of ignore those. And what we obtain is that this is just 1/2 e to the 2jt plus e to the 3jt. And we observe here that all of the answer choices, well, it's okay, first of all, it's clearly not this one. And all of the answer choices has a cosine in it. So this is the point where like you want to use the answer choices, like the answer choice format to your advantage in order to obtain your answer. So the answer choices demands us to put in the cosine format. We will do so. And so I will factor out e to the 5/2jt. And then what I obtain in the inside is e to the negative 1/2 jt plus e to the 1/2 jt. Then we have we have e to the 5/2 jt, and then we have 1/2, we have e to the jt and the same numbers. This is just purely cosine of 1/2 t. And that is our answer. Questions, comments, concerns? Remember, I'd be happy to answer any. Otherwise, I'm going to keep powering through. 26. If the input the following, it produces the output of that from an LTI system whose impulse response is real. Oh, that sounds important. Impulse response is real. then what is the output from the same system when the input is that? Okay, and so probably the most important thing here is to realize that, again, this uses the eigenfunction proper. I mean, you could do a Fourier transform approach, but the Fourier transform approach will be extremely will it be algebraically? I believe it will be algebraically kind of more complex, which is why I don't want to do it. But instead, I'll show you the eigenfunction way. And so we know that if I input, again, by eigenfunction, we know that if I input this, then it has to be something in the format of some number followed by e to the negative 2jt. And what we observe is that, wait a minute, isn't that just like literally just that? We have e to the 4j, e to the negative 2jt. Well, what do you know? That was very easy. We just found out h of negative 2. Furthermore, if I input this into my system, I should recover something that looks like this. But what do you know? We could literally just recover h of 3 to be as follows. Voila. And so now we know that h of 2 is equal to 4e to the 4j, and h of 3 is 2 e to the negative 3j. Not too shabby. And so now the question is, what if I input this then it should be very clear that my output should be something that looks like this. Oh. Wait. Yeah. All right. And recall that if h of t is real, this directly implies that h of omega is equal to h of negative omega. This is a fact. I'm pretty sure it was proved in lecture, but if x of t is real, purely real, then we know that actually, it should be something like this. Wait, I literally wrote the same thing twice. I don't know what my apologies. Should be something like this. There we go. This is a true fact. And so now this means that this is equal to h of negative 2 conjugate. Same thing as before. H of 3 conjugate. Same thing as before. And we can obtain the conjugates by just conjugating directly the number, by just taking the negative of the exponent, because that's how Euler form works. And we obtain our final answer very, very quickly. And thus we obtain our answer. Questions. If the question said it was even instead of real, would h of 2 be the same as h of negative 2? No. We would need the function to be real and even for, I mean, hold on. Let me think about that. I believe so. I believe you're right. Yes. Actually, hold on. Yes. Yes, you are correct. If the question said it was even, then h of 2 would just be equal to h of negative 2. All right, next question. Consider the following sinusoidal steady state circuit with a voltage source V of t. What is the value of the current I of t if V of t is that? And what are even and real functions? Or what are even real function? Even functions are functions such that x of t, I'm sectioning this off, f of t is even and is defined to be when f of t is equal to f of negative t for all t in R. Of course, by single value functions. It's just symmetric and non-imaginary. That's basically, yeah. That's basically it. Okay, I guess I don't even need to write this down. Yeah. Real functions means that the output is always real. No, no imaginary. For this particular question, you could do it in two different ways. And I'll be honest, I'll do both ways. I will do both ways. Well, first of all, we know that V equals IR or V equals IZ. This is true. Or more so like by, sorry. And let's convert the voltages. Let's convert the input signal into a phasor form. There's 4 cosine of 2t, so it's e to the jt. Sorry, just 4. I believe it's literally just 4. Yeah. And then this is 2. Wait, what in the world? Hold on. E to the j0, yeah. Wait, am I? Yeah, e to the jt. Yeah, okay. So this would yield us a phasor form of 4, and this would yield us a phasor form of 2. Yeah, thank you. Thank you. Sorry, it's been a while since I've done this, so a little rusty. So now we have to deal with both of these very independently. And so let's consider this one to be 1 and this one to be 2. 1. Well, we have that V is equal to Z I times Z L, or maybe I'll write that somewhere else. And this means that our current phasor is this. So this means that this is just 4 over ZL, which is omega equals 2 here, omega equals 3 here. So sorry, I just want to be very coherent here. I is equal to omega 4 over j omega L, which is just equal to 1 over JL, which is just 2J. And then our second current, omega equals 3, I is equal to, did I just, hold on, sorry, what in the world did I just do? I just canceled nothing out for no reason. Yeah, sorry. 4, 2, so there's 4 over 4J, which is equal to 1 over J. Sorry, yeah. I had an extra 2 right there. Yeah, thank you, yeah. For this next one, we have 2 over J omega L, which is equal to 2 over 6J, which is equal to 1 over 3J. And I will convert this to polar form. And so now we have the polar form. So one, we have the phasor form. The phasor form obtains us a cosine function that is t minus t plus pi over 2. Oh, sorry. Sorry, no, it should be, yeah, t plus pi over 2. Hold on. No, it should be t minus pi over 2. Wait. Sorry, I always get confused on this part. I just need to make sure it's consistent with my intuition. Yeah, it should be t minus pi over 2. Yeah. Is it a plus? I believe not. Also, it should be 2. Sorry, it should be 2 times. Should be plus. I mean, okay, well, the thing is that like I write it out like this, but my initial gut reaction is the fact that this is a phasor that starts down here. So like my immediate translation is that this phasor immediately gives us sine of t or sine of omega t, whatever the encoded frequency is. And so one should immediately just give us sine of 2t, and 2 should immediately just give us 1/3 sine of 3t. Sorry, I'm just very bad at I'm still haven't like solidified converting between sine and cosine because I never really found the need to what do you call it? Just like memorize how it works. And so, but I just like to do this kind of conversion, which helps out very nicely. And so what we get is that it's just all we just need to do is add 1 plus 2 together, and we obtain our answer. That is all. I will. That's very weird. That's very weird. I believe that it is indeed. See, sine of t is equal to cosine of t minus pi over 2. Yeah, because sine of 0 is equal to cosine of negative pi over 2. And then like it follows indefinitely. Like one starts like this and the other starts like this. And so yeah, you consider this gap. And so I believe it should be negative. Okay. Yeah, thank you. Okay. By the way, it's important to just have like different ways of confirming these kinds of translations because you get even I get like confused sometimes. Regardless. Okay, problem 28. Suppose x of t is a sum of complex exponential. Yes, exactly. A good point, Tiger, is that that was actually what dilemma I was having is that do I want to do it the normal ec45 way? Or in fact, you could literally just take um the current voltage relationship of an inductor and just directly take the derivative. And I think that will save you more time. It really depends, right? All you would need to do is just take the integral of this function. Yeah, all you just need to do is take the integral of this, because I of t is equal to the integral of 1 over L vt dt. So you could just you could just do that, and that will save you a lot of time. Or do that. 28. We have a sum of complex exponentials, which should be now a signal to your brain saying like, oh, either it's an eigenfunction property or we're going to use that as delta functions. One or the other. And it's input to an LTI system with the following frequency response of that. Oh, what? Okay, it's exponential Fourier series. What is those? Okay. So take a gander here. Well, our output signal is clearly just this. And in fact, I will not even do that approach. I realize that, again, eigenfunction y of t will be equal to 2 times, because since I've done this so many times, I'm just going to directly write it, and hopefully it is clear. Minus 4h4 e to the 4jt. So yeah, we've done this many times now. And now all we need to do is expand this. It is just purely omega. And so this is just, oh, it's negative 4 e to the this plus h of 3. Hold on. Should be 6 e to the this minus hold on. Uh Wait, why am I blanking on this? It should just be this. Sorry, why I don't know why I blanked on that. There we go. So we obtained this kind of sequence. And now here's like kind of like the little intricacy here is that could like we intuitively understand that, well, this has period, or this has omega equal to 2, like this has period to be pi. This has period pi. And this has period pi over 2. Then you will immediately, like, it is true, it is objectively true that you could say this has period like 2 pi. Oh, sorry. You could say that this has period, this has period, yeah, you could say that this has period 2 pi. It's technically true. It's like saying, oh, sine has a period of 4. It's not false. Like, it's not false that, you know, it does repeat every 4 pi. But um, I believe that the intricate part about periods is that we're taking the smallest number such that this, so we're taking the smallest number such that this repeats. So take period such that, sorry, take minimum number t such that f of t plus big T is equal to f of little t as our period. So that's the intricacy here. Like we don't want the willy-nilly, oh, but it could be, but the period could be 8 pi. No. We will just say that if the smallest number such that the such that its periodic is pi, then we'll say that the period is pi. That is all. Y that equals that. Oh, it's because h of negative 2 is equal to 2. I'm sorry, h of negative 2 is equal to negative 2. Go. And so because we know that the period is pi, or yeah, we say the period is pi, then if t equals pi, then y of t is equal to, obviously it's a Fourier series, right? I mean, I guess you could do it in so many different ways. Whatever. It's equal to n equals n and z e to the j e to the j n pi t. Wait, no. Jn omega not t. So it's Jn 2t. There we go. And we realize that y of -1 is equal to -4, and y of 1 is equal to 6, and y of 2 is equal to -16. And so all we need to do is take this one and this one and sum them up, and we get -20. There we go. There's our answer, our desired answer. Next question. So we have 7 more now, I believe. Remember, please feel free to ask questions, and please feel free to interrupt, and I'd be happy to answer them. If the signal x of t is periodic with period 16, and its non-zero Fourier series coefficients are x of 2 and x of -2 equal to 1. That should tell us a lot. And then which of the following is a signal? Well, x of t is equal to, well, first of all, t equals 16. Then omega naught is equal to pi over 8. Yeah. And so now what we obtain is that x of t is quite literally just e to the 2 pi over 8 t plus 2 -2 pi over 8 t plus j e 4 pi over 8 t plus j e to the 4 -4 pi over 8 t. Any questions so far? This is, I'm like, all I did was I just said I am given a periodic function and the Fourier series. I just decompose it into this, it's like its components. It's just like into just this. I forgot every single j. There we go. That looks a lot better. And so let's just simplify this. E to the pi over 4 j pi over 4t plus e to the negative j pi over 4t. That should look familiar. I will edit this so that it looks a little nicer. Or actually, I won't edit it because the question is kind of baiting me. But we do e to the j pi over 2t plus e to the j pi over 2t negative. Voila. What is this? This is 2 times cosine of pi over 4t plus 2j cosine of pi over 2t. And we get our desired answer. That's it. That is all. Questions, comments, concerns. And the question is, how do I know it's cosine? And how do I know to like not rearrange the cosine? Again, the rearrangement between the rearranging from complex numbers from cosine to sine is entirely contingent upon observing these numbers and observing the sign. So I say, oh, the exponentials are the same. Then is the sign positive? Then it's cosine. If the sign is negative, then it's sine. That is all. And that, again, that directly comes from the fact that the Euler decompositions of both functions. Any questions so far? I actually want to take like a very short pause here because I feel like I was really powering through. I want to give everyone an opportunity to kind of like maybe go back to question. I'd be happy to, or re-elaborate some concepts since I was going really quickly. Maybe I'll go a little slower next time. Thank you. At this rate, we'll be finishing within 3 hours, which sounds fair. So like you'll see that this exam is indeed designed to be done with under 3 hours. In fact, you actually have less time than 3 hours. So, pardon? Okay. I mean, if there's no question, I'm gonna keep going. But otherwise, please feel free to unmute, and I will be happy to answer them. let f of t be a sum of deltas. If g of t is obtained by convolving f of t with itself 3 times, then what is that following function? Okay. Okay. Obviously, okay, it's very clear that I could brute force this question. I will try to think of a very clever. I'm just taking a pause because I don't think of a clever way to do this. Maybe. Okay, I'll do like this. We know. I just want to see which way is the most optimal. We know that pi of omega of t is equal to, or has a Fourier transform 1. F of t will have a Fourier transform of 2 plus 5 times e to d. Oh, wait, what was it? It is e to d negative j omega 1. So just j omega. Because this is like by the time shift property. If I'm translating by t naught, then I have to modulate, not modulate it, but I have to multiply by complex exponential in the frequency domain. That is one of the properties that we learned. Okay. And now if I convolve this 3 times, then we know that g of omega is just f omega cubed. And furthermore, this integral hold on, let me just think about this for a second. Oh, wait, I don't think I have something very nice. Huh. Yeah, never mind. I guess I'll just do a normal approach. I think the normal approach is the best way. So I have this. And so let's take a chill pill and let's take it step by step. I'm convolving 2 times delta at 0 plus 5 delta at 1. 2 delta at 0 plus 5 delta at 1 convolved with f of t. And now we'll do these. I'll do the first two first. And so remember how we convolve delta functions. We want to do in the very most optimal manner possible. We do like polynomials. This is 4 delta at 0 plus we do FOIL. So the insides and outsides will both become delta at 1. So it's 20 delta at 1 plus 25 delta at 2. And now we convolve that again with 2 delta at 0, 5 delta at 1. Okay? So now we could write this entirely out. You have 6 delta at 0 plus 40 delta at 1 plus 25. No. Sorry, my deltas look like 8s, which is actually a shame. I'll make him look like more like a bean. Yeah, sorry. Actually, maybe I should start fixing my deltas. My deltas have been looking awfully like 8s. Okay. Okay. And then there's 50 delta at 2 plus 20 delta at 0 plus 100 delta at 2. This is delta at 1 plus 25, 125 delta at 3. All right, so this is our expansion. And I did that very, very quickly, like in retrospect, right? Like I just convolved three different functions under 2 minutes. I just have to write it out. And so now I want to take the products. First of all, g of t is defined to be like that, and I want to see what falls into here. Well, pi over 2, this is less than 2, strictly less than 2. This is strictly greater than 1. Sorry. This is like this. Wait. Hold on. Yeah. And so basically what happens here is that every delta function we're integrating, like remember, we're integrating from on the number line, we're integrating from pi over 4 to pi over 2. And the only integer that falls inside is 1. And so we only care about these two. Is that clear to everyone? Like, I really wish, I really hope, if it's in the first term, 8 delta. Yes. Thank you. I hope it's really clear that, like, when you integrate over delta functions, you only care about which one falls into the interval of integration. And since we're integrating from pi over 4 to pi over 2, the only thing we care about is this one and this one that falls into that interval. And everything else goes to 0. And so this is just equal to gt. Well, it's just, what is this? It's the same exact thing as integrating over delta of t minus 1 plus 60 delta t minus 1 e to the j pi t dt 60 times e to the j pi, which is equal to negative 60. Voila. Amazing. So it's just important to kind of really understand the relationship between how delta functions interact with the integral. Anyways, problem 31. If sine of 2t is the input of the LTI system whose frequency and magnitude plot are shown below, then what is the output signal? Okay. So first of all, let's actually just straight up just plot out what sine of 2t would look like on the frequency domain. So I will actually get my blue out. And then let's call this x of t. Then x of omega would look like as follows. It would be, I'll just show you where it's placed. Place right here, place right here. Or like, I wouldn't say it's like lives right there. It's like kind of like lives here. And how do I put this? So again, this kind of question, you could kind of interpret it in two different ways. You could either take it to, can you explain why it's only delta 1? Because, okay, actually, let me actually elaborate on that. I think it's going to be very valuable. So currently, my function is like this. It's some number here. It's some number here. It's just 4 impulses. I'm going to actually space them out even more. In fact, I'm actually going to just get rid of half the plane. t, g of t. There we go. And where am I integrating? I'm integrating from pi over 4, which is somewhere over here, to pi over 2, which is somewhere over there. And then, which means that the only one I care about is this one right here, which is delta 1. That's why we're only taking delta 1. Anywho, I'm sorry, my eyes hurt a little bit, but that's all right. So I'm gonna examine this question. I think the best way to approach this question is by using it again an eigenfunction property. We know that x of t is equal to e to the pi over j e to the 2jt plus minus pi over j e to the negative 2jt. This is just what we know about our current input signal. And this means that our output, after we input it into the output, because of our eigenfunction property again, we know that our output will be the magnitude times whatever this was, or I'll just say h of omega. H of 2 e to the 2jt, and then we can just figure out h of omega later. H of negative 2 e to the negative 2jt. There we go. Voila. All we need to do is solve for h of 2 and h of negative 2. So h of 2 has magnitude. Actually, yeah. H of 2 is magnitude of some number, an angle of some number. It is precisely 2/3, sorry, 1/3 magnitude, and angle is pi over 4. So remember the slope is pi over 4 here. Slope pi over 4. The slope here. The slope here is 3. Like it's negative 3 and then 3 here. So take that as you will. Oh my God, it's not 3. It's actually negative 1/3. Sorry, I got tripped by the scaling. Please be careful of scaling. Anywho, and that one's also right. That's good. And so for this should be pi over 2. Therefore, we know that this is just equal to 1/3 e to the pi over 2 j. Similarly, h of negative 2 will follow similarly, where it is, sorry, my neck hurts a little. We could obtain the magnitude, and we could obtain the angle separately using the graphs. I believe it's 1/3 again, and this is negative 1. So this, combine these two again, and we get 1/3 e to the negative pi over 3j. And so, thus, our output should be pi over j. It's actually just 1/3. 1 over 3. 1 over 3j. This is 1/3 j. So this is 1/3 j e to the this minus pi over 2 pi over j 1 over 3j. Actually, maybe I'll leave it as like negative 3j. There we go. So this is plus now. I'm just organizing as I like. And then now we realize that a bunch of things cancel out. Oh my, it's gonna overflow. That's not fun. So I've been writing a little big. This is equal to pi over 3 e to the 2jt plus, oh, what do you know? It's again pi over 3 e to the negative 2jt. This is just pi over 6 cosine of 2t. Therefore, we can obtain our answer. Oh, sorry, that should be, wait, hold up. What did I mess up? Yeah, this should be, wait, wait a minute. Pi over 4, that's good. Pi over, slope is pi over 4. That's fine. Pi over 2, that's good. Yeah, wait, actually, no, I think I'm fine. Pi over 3. Hold up. Wait. Where did I get obtained the oh, oh wait, I don't know how in the world I put pi's there. It should be all just be 1 here. Sorry, I thought of the yeah, I thought of the Fourier transform. I was directly converting it to the Euler form, which I don't need pi. That's very important to play. Please don't get confused on these. Probably that. It's probably yeah. To convert your sine input into cosine, not necessarily, because the issue here is that hold on. So I would not like to work with that necessarily. Okay, so I'll first finish this question and then I'll address the question in the chat. So I don't need, I need to get rid of all those. Yeah, sorry, I need to fix all my numbers here. There we go. Yep, there we go. 1 over 2j. 1 over 2j. Get rid of that. 1 over 2 over 6. 1 over 6. And therefore that is just 1 over 2, 3. There we go. And then we obtain our final answer. So the question says, shouldn't you, when converting the sign, should it be not just one? Yeah. I just did that. Perfect. So the question says, would it be easier to just use the property where if your input is cosine of omega t, then your output is just cosine of t, you can't convert your sine input to the, oh wait, actually, yeah, that's actually kind of true. Or not necessarily. So, let me actually think about that. No. Yes and no. So for this particular problem, yes. So a question in the comments said, can we just do, I actually intentionally avoided that method because of the following reason. Couldn't we just do this? And for this particular question, yes, you can. Like because it's precisely because our transfer function is in this kind of format where the angle, like how do you call it? Because h of omega, like you would need more justification. To do this, you need that h of omega is equal to h of negative omega star. And with this observation, you could just do that. So this is an alternative method. You need this, but since this is true, you could do this. But this is not true in general. That is the most important part. Because this, you need this to be true. Otherwise you cannot do that. Because you could show it algebraically, but if you decompose Like this only works because if you decompose into eigenfunctions and then you multiply by like whatever whatever you multiply by the eigenfunction with, and you recombine them, and then you obtain this kind of answer. Otherwise, you cannot. Like, this is extremely important. Otherwise, yeah. So, just so you know, I feel like, but this is such a like a small case. It's better to kind of work out why you essentially by doing this method, you basically you basically showed this. But yeah, I feel like it's better to work out this kind of method and do the nitty gritty and understand the eigenfunctions. But yeah, but otherwise, the comment is true. Whew, all right. 33 to 34, 35. 5 more problems. The input signal x of t in the system below has Fourier transform x of omega. Also the Fourier transform h of t. Wait, okay. What is the Fourier transform of y of omega of the output signal? Okay. And so this is clearly a sampling problem. So let's actually take a gander at it. Hold on, okay. So first of all, it's important to note that this yields a Fourier series Fourier transform. As follows. For t 4n. I lied, it should actually be omega. There we go. And so what does this mean? We're gonna place copies of x of omega out by 4. That's just wrong. There's our first one, anchored at 0. And what do I want to do? So the thing is, like, since I'm cutting off up until 3, I only need to consider the graphs of the functions within these bounds. And so I will do that. Remember, I'm spacing out by 4, I believe. So I'm gonna go right here. That's 2, so that's right here. I'll draw another function. 2, one more, go up. And then I'm just gonna draw the rest of it to scale, but you get the idea. And then I'm gonna draw my last one in blue. It should be at 4. So I go left by 1, go up, and then I go down. Voila. Perfect. That looks right. So now let's go into our analysis directly. What I want to do is also remember that all of these heights are scaled. So this height right here is 4, this height right here is 8. And so after that, I want to add all these up, and I want to just cut it off by like this. And so what happens is in purple, I'll draw it in purple, I just want to consider everything between here to here because that's all I'm taking. Everything else goes to 0. And remember, I'm multiplying it by 1, so it preserves height. This low-pass filter preserves height. But it zeroes everything else here, so remember. And so I'll do exactly that. I will add everything together. I have 12. I have the same exact thing. I have 1, and I have 1 more. So that's my graph. The purple graph is what I want. This is 12. And so pick the purple graph. There we go. Oh wait, why is there pi there, huh? Did I forget a pi? Oh, sorry, I forgot that I have to divide everything by 2 pi. 12 pi over 2 pi, 8 pi over 2 pi, and 4 pi over 4 over 2 pi. Because I kind of forgot that recall that x of omega convolved with s of omega. Like we need to keep this. I forgot the 1 over 2 pi factor. So yeah. There we go. Oh yeah, yeah. Thank you, Sam. And so I got that part, perfect. And then which yields us exactly this answer. Perfect. And so figure A. All right. Oh, 3 more questions. 4 more. Suppose the bilateral Laplace transform of a single signal s of x of t is, okay, which is known to converge at e to the j pi over 4. What is the value of that? Ooh, okay. Is there a smart way? I doubt it. I feel like we need to just go ahead and just calculate the Laplace transform. So we know that x of s is equal to 1 over s minus s squared, s squared minus s. And we will, you do partial fraction decomposition. We know that, well, in my head, like there's a very actually simple way to do it, in my opinion, for this specific question. So we broke it up into 2 different addends. And all we need to do is find coefficients. We know that the numerator is 1. How can I combine these 2 such that it's just equal to 1? Well, my immediate reaction is just taking, oh, I do s minus 1. This is equal to 1. So I just take a equals 1 and b equals, a equals -1 and b equals 1. Of course, this kind of argument this kind of like intuition comes from doing partial fraction decompositions countless times, not even 20b, but like more than 20b. And so I'll just actually just work it out. So we know that a times s, so a times s plus b times s minus 1 is equal to 1. A plus b s plus, or something like that. Hold on. Sorry. To fix my eyes, minus b is equal to 1. And so what this means is that a plus b must be equal to 0, and negative b must be equal to 1. This tells us that b is equal to, wait, this feels extremely incorrect. I'll probably see what's wrong later. This just means that b is equal to -1. And then this must mean that a is equal to 1. And that actually works out very, very nicely. Yeah, okay, there we go. Okay, that gives us the exact flip of what I did before. I think the easiest way is just picking S0. Yeah, exactly. Like you just want to pick values of S, like for this specific type, but working out the math also is very nice. Either way, we obtained our conversion. And so now, and remember that this lies in our S equals j pi over 4, which is equal to square root 2 plus square root 2j, and it converges here. If our Laplace transform converges here, then, okay, well, let's actually draw a region of convergence. I know that's way too big, but it doesn't really matter. Our regions of convergence, or our kind of like axes of convergence, I like to think about it, are right here and right here. And we know that it's going to converge somewhere over here. Then, wouldn't it make sense that the blue line is anti-causal, and the red line is causal. So again, these kind of questions have a very strategic way to do it. When you're given that it converges at a certain point, you have to pick which one is causal, which one's anti-causal based on where it converges. And so we realize that the red one is causal. So with the causal assumption, we do the inverse Laplace transform of 1 over s minus 1, which is off the top of my head, it should be e to the negative t ut. I hope that is right. Actually, let me just check. I don't want to be too wrong here. No, it should be just t. Yeah, it should be just t. Yeah, it should be just t. And I want an anti-causal 1 over 1 over s, or negative 1 over s, which yields us, it should just be like u, it should just be like u of negative t, I believe. And so what we obtain is that the x of t is equal to e to the t ut plus e to the this. Yes.
Shouldn't the 1 over s minus 1 be the anti-causal case because it's going to the left because s is centered at 1 and then it converges at the left of its.
Oh, yeah. Wait, actually, that's a good point. I completely mixed it up. I'm sorry. This is true. My apologies. There we go. Thank you for correcting. So if I have anti-causal s minus 1, then I would have negative e to the negative e to the negative t. No, it should just be t. Negative e to t, u of negative t. And this should have a transform of just u of t. Yeah, I believe that is consistent.
The negative would carry on to the u of t.
Oh yeah,
right?
thank you. Yeah, I kind of forgot. Boom. Perfect. And so now we could just solve for whatever we wanted before. X of 1, negative 1 is equal to e to negative 1. Oh, but this one goes to 0. And so we would only take negative 1. And x of 1 would be equal to, we only evaluate this. Let me actually color code it. And so the sum would be negative 1 minus e. And okay, wait, hold on. I clearly messed up somewhere. I believe I messed up on.
You didn't carry on the negative in the anti-causal one. The e to the.
Oh, wait, hold on.
You flipped the negative, so it would be
The anti-causal
negative e
one?
to the t u of negative t minus u of t, right?
E to the negative t?
Oh no, it's negative e to the t u of negative t
Yeah.
minus
Oh yeah.
u of
Oh
t.
yeah. I didn't change. Oh, that's what you meant. I didn't change this. I didn't change the causal part. Okay. Thank you.
I got you.
Yeah. Perfect. So, then I want what I want. I want this to be negative 1. So this is negative 1. And then red. This would be e to the negative e to negative 1. Perfect. So if I sum these two together, then I'll get negative 1 minus 1 over e, and thus this would be indeed e over minus plus 1. And I believe this is our consistent answer. Perfect. Thank you very much. All right. Any questions so far? We have like 3 more questions after this, so just want to take a short pause. Any questions? Let me check the chat. Okay. All right. All right, let's wrap this up. What is the following function? What is the following function of t equal to? Okay. Let me take a look at this. Hold on. It looks very daunting at first. Okay, so my first reaction is that we're integrating over omega. And omega squared. Damn, this one's not really fun. Okay, so first of all, it's actually very clear that this is actually just a inverse Fourier transform of this function. I hope everyone sees this, but this is just this. Or well, it's 2 pi times that. So this is equal. So if f of t if f of omega is equal to 3 pi squared plus omega 1, then, and this has a Fourier transform, f of t, this is literally just 2 pi times f of t. So this one's like the really important first observation that we need to see, is that you could just decompose this and represent this as just a time domain function. And so now all it suffices us for us to do is to kind of find out what the inverse Fourier transform of that is, which doesn't look too fun. The thing is that okay, so me personally, if I found this on the exam, I wrote down the Fourier transform of, like, I'm pretty sure, wait, I'm looking at my cheat sheet right now from like 3 years ago. And on the cheat sheet, I have the Fourier transform of e to the, like something t, like e to the a t there. So like, I'm trying to think about how, from any like a normal scenario, I would kind of try to mess around with this. But I could see how I would approach this. So yeah, I think I just need to take an inverse Fourier transform of that. I think maybe writing it out will be a little nicer. 9 pi squared plus omega cubed. Okay. Omega squared over that. Yeah, it seems Laplace s equals j omega. Maybe? Can you elaborate on that? S equals j omega. Is there a way to do that? Why is it 3 squared? Oh wait. Oh wait, yeah, that's a good point. Sorry. I don't know. There we go. Huh. Trying to think about this. Yeah, because it's funny because I straight up have it listed that e to the t is equal, like, has a Fourier transform of 2 1 plus omega. So I could probably manipulate this, but that is just cheating, in my opinion. Let's try to crank this out in a very smart way. Or hopefully I don't have to brute force this. Oh, okay. So I'll take the following approach. I hope way back in class, if it's cosine, it's a cosine if s equals just j omega. Can you elaborate? It's a cosine if s equals j omega. I can kind of see what you're saying. But not really. You have to get a cosine form. S equals j omega. Hold on. Like, I don't know how to solve it from there though. Oh, I still don't see how you would manipulate it. Uh, if you have to manipulate, but you get a cosine. If S equals j omega. So what you're telling me is that I'm trying to do this. Um, and then I let S. The only issue with that is that maybe like I could pull out a J here and say this is ds negative. I think it's negative J actually. Look at the answer. It looks like. Yeah, it's a Fourier transform pair, but you know that kind of feels like cheating. And so, or I mean, it's nice if you wrote it down, but I feel like it's important for us to kind of review and see why or how it works. And I will invoke something very small thing that Professor Ziegler said in that partial fractional decomposition is very powerful. And so let's actually check it out. I could actually change this into, or not even change it. I could just kind of write it out as negative j j omega squared, or more so, minus j omega 1 over root 3 squared. There we go. So we could represent this as a difference of squares, which is convenient. Now from this point, I could use partial fraction decomposition and change it to two little things. So now it's a divided by pi squared 3 plus 1 over squared 3. Actually, here, let me make this easy and do this. There we go. That makes it way easier to compute for us. And so this is 9, 3 pi. Oh yeah, that is so much easier. And then plus minus j omega squared. And now this is a difference of squares. And so we could represent this as a sum of two fractions. Okay, and all we need to do is solve for the, oh, and then what I would do is I would just take, and I know that a 3 pi minus j omega plus b 3 pi plus j omega is equal to 3. Whew. And so what this means is that 3 pi a plus b is equal to 3, and a minus b, a has to be equal to b. Or yeah, like I'll just write it out. Negative aj omega plus bj omega is equal to 0, which implies that a is equal to b. And so all we need to take, what is putting the j in there? I know they equal the same thing, but why, I don't know why would it help. Oh, it's because you'll see. Uh, I mean, well, I feel like this is originally how we derived the Fourier transform of that function. So like in order to go the other way, you have to use partial fractions, or I recall that was the original way. And so let's keep going. Where am I? Oh yeah. So I want to take a equal to b. Wait. Yeah. I want to take a equal to b. And so I will take a equal to b equal to I believe it's 1/2 pi, I believe. And so I just take that. Actually, I'll just leave this. So now we have f of omega is equal to 1/6 pi of 1/3 pi plus j omega plus 1/3 pi minus j omega. Okay? So now we have this. And from here, it's actually very easy because we know the inverse Fourier transform of this and this. Oh, sorry, 1/2 pi. Pardon? Sorry, my eye is hurting. Sorry. 1/2 pi where? I don't. Oh, sorry. Yeah, you're right. Sorry. I don't know why I put 1/6 pi. That would be equal to 1 then. Thank you. And now from here, now we have a sum of these two things, and this looks very similar to 1/a plus j omega, or a minus j omega, whatever. And so, well, we could kind of use our known Fourier transform pairs, in that now this is like 1/2 pi of this plus 1/2 pi of this. So we have this kind of function. And let me just make sure to check with my appropriate thing. And I could convert this. This has a Fourier transform specifically of e to the -3 pi t u of t. I think it's multiplied by 1/2 pi, I believe. Hold on. Maybe I think I missed out on 2 pi somewhere. Oh, there we go. There we go. Okay. So I'm fine. I'm doing fine. I'm doing fine so far. This has that. And then this has a Fourier transform of 1/2 pi e to the positive gt ut. And combining these two, we realize that this is literally just e to the pi of absolute value of t, -3t. Perfect. Isn't that nice? That feels nice. And so now we declared up here that this integral is equal to 2 pi f of t. Then our answer is equal to 2 pi times f of t, which is just equal to the following. So yes, it is true that if you had the Fourier transform written down, it would have been so much nicer. But please realize that this kind of work is doable in like 5-6 minutes. If you like the partial fraction decomposition, and I know these Fourier transform pairs. And so this is doable. This isn't like some demon question that we would want you to like just not solve. No. This is a question that's completely solvable. And which is why I like did the algebra and to show you that like, oh, it's actually not too complex. And this was actually, I believe this was also done in class. So yeah, that is our answer. Cool question. I like that. It really was a nice algebraic exercise. Anyways, problem 35. If the output of an LTI system is that, when the input is the following, what is the impulse response of a system? Great question. Well, we know that the impulse response, well, we can actually directly compute the frequency response as follows. One over I believe, no, I believe it's just 2, not -2. There we go. Yeah. And then Okay, there we go. We literally just computed like um our frequency response. And furthermore, we could actually expand this to be 2 plus j omega. This is like one of the cheat codes or like you have to see it once to do it again. It's like when I first saw it, I was like, wait, you could do that. But in reality, it's just like you're just rearranging numerators. You realize that this is just 1 plus 3 over 2 plus j omega. And the Fourier transform of this would be delta t plus 3 times e to the negative 2t u of t. And thus we get our answer. Questions? Would it be better to convert S domain to this one, or is that not allowed? You can. Yeah, you can. Um, hmm. Yeah, I believe you can. Or can you? Actually, let's try that. Let's try doing an S domain. We have 1 over S plus 2 over 1 over, so it's the same thing. It's just 2 plus S over, no, 5 plus S over 2 plus S. Then that would be 1 plus 3 over 2 plus S. And then we would get the Laplace transform, it would be delta of t plus 3 e to the, yeah, it'd be the same. Radical. Well, the only thing is that um, uh, like you don't necessarily have information regarding like the causality or anti-causality. Um, and so which is why like it'll be a little iffy. But I mean, if the algebra worked for you, then like it'll be fine. And furthermore, all the answer choices say it's just normal U of t. And so in this case, yes, it would be fine. But yeah, this would be the intended route. Oh, and that's it. What in the world? Where's the, I thought there was 36. Well, I guess this is 35 questions. That is all. Thank you for coming. And are there any other questions, or otherwise I'll end the meeting? If I see the number of participants drop significantly, I'll just pause the recording. Otherwise, I'd be happy to answer questions.
I have a question.
Yes.
So I'm confused as to what the S domain actually represents, because all I'm seeing the difference between like all I'm seeing is that S is equal to JW in a sense.
Yes.
Like, what does that mean?
Like, so this is like just a conceptual question of what is the significance of the Laplace transform?
In a sense, but also just because yeah, in a sense, I'm just confused as to like why we convert it into an S domain if we could just do it in a frequency domain, I guess, right? Because it's 1 over 2 plus j omega, but you can also just do 1 over 2 plus S, right? So like the transforms look pretty
Pretty similar.
identical.
This is true.
Yeah.
How do I want to put it? First of all, I have a question in the chat. Recordings will be put in like they will be uploaded onto Zoom right after this meeting ends, and I will send the link via Piazza. And the notes will be posted on the notes section of Canvas. I'm just gonna okay. So what is the point of the Laplace transform? Good question.
Is it just because it's like simpler notation, perhaps?
No, not necessarily. So first of all, it's important to realize that the Laplace transform is like the dad. It engulfs the Fourier transform. Like anything with a Fourier transform will have a Laplace transform. The only issue with the Laplace transform, from what I can see, oh sorry, with the Fourier transform is hold on, let me think about this. This is a good question. First let me end the recording. Just because like there's some you can't take a Fourier transform of a function that blows up, so you try to make a ft of e to the at and ut would blow up. That's true. Hold on, okay. Stop cloud recording.